In this video, we're going to be talking about representations, and as the title of the book suggests, introduction to Lie algebras and representation theory, representations are going to be a key focus of our studies. And so with that being said, let's take a look at the definition of a Lie algebra homomorphism, which will segue right into the definition of a representation. So definition: let L and K be two Lie algebras over the same field F. A linear map phi from L into K is called a homomorphism if for all x and y in L, phi of the bracket of x and y is equal to the bracket of 5x with phi of y. And so just to be pedantic, this bracket on the inside here is in L, and this bracket here on the right-hand side is in K. Okay? In particular, a homomorphism is called a monomorphism if it's injective, an epimorphism if it's surjective, and an isomorphism if it's bijective. Hopefully these definitions aren't too novel to you. You've probably seen them in abstract algebra for rings and groups, and so and also for algebras, and so this extends naturally for Lie algebras. We've actually, in fact, already seen the isomorphism of a Lie algebra in an earlier video, and so now we're restricting that notion to what if you're just injective and what if you're just surjective. Okay, and so with that being said, let's take a look at a couple of examples. Example 1 is this going to be the zero map. Okay, so if we say L is some Lie algebra and K is just the zero space, right, with trivial bracket, then the map theta that sends L into K, where theta of x is always sent to 0, well, this is going to be homomorphism because, well, theta of 0 is going to always equal the theta of x bracket y, right, because x bracket y is just going to be sent to 0. But on the other hand, we also have that theta of x bracket theta of y is going to equal 0 bracket 0, c equal to 0. So these two guys agree, and so it's a homomorphism where I've implicitly already assumed this map is linear because, well, it's obviously linear. Okay, the second example, maybe a slightly more interesting example here, is going to be to the trace, right? So the trace is a map that goes from GL and C, just the sum of the diagonal entries, into the complex numbers. And here we're treating the complex numbers as a Lie algebra endowed with your standard bracket, where you take two numbers, multiply them, and then swap the order, and then take the difference. So it's all the bracket here is always going to be 0, right? If complex numbers commute, and so let's check that this is actually a homomorphism. So the linear map part is already satisfied. We know the trace is linear, so let's check if it preserves the bracket structure. So if I have x and y in GL of NC, then let's see what the trace of x bracket y is equal to. Well, that's precisely equal to the trace of xy minus yx. Now by the linearity of the trace, there's a trace of xy minus trace yx. Now the trace is symmetric, and so this is equal to 0. Okay, now let's try it the other way. What happens if I take the trace first and then I bracket? Well, this is just going to equal trace of x, trace of y, minus trace of y, trace of x. And these guys are just complex numbers, so of course they commute. It's going to equal 0. Okay, so what that tells us is actually, let me switch colors here, is that these two guys here are equal. Okay, and so we have that the trace is a homomorphism. Okay, now the third thing I'm going to talk about is actually let I be an ideal of L. Then we have something called the canonical map. And we'll almost always denote the canonical map with the letter pi. And the pi map is going to go from L into the quotient algebra we defined last time. And what it's going to do is it's going to send a vector x to the coset x plus I. Okay? So this map will prove to be really useful, especially if we're smart with our choice of ideal. And so let's see that this map preserves the bracket. So let's start off with pi of x bracket y for two arbitrary vectors in x and y in L. And so this guy, by definition, is going to be x bracket y plus I. Now, on the other hand, let's see what happens if we take the bracket second. This is going to equal, well, pi of x, by definition, this is x plus I bracket y plus I. And then by the definition of the bracket in the quotient algebra, this is simply x bracket y plus I, which we saw was well defined last time. And so these two guys agree, and so we see that this satisfies the preservation of the bracket. I'll leave it to the viewer to check that it's a linear map. That's not that enlightening. Okay. And so we're going to come back to these examples momentarily, but let's take a look at a quick fact. So here's a fact. If phi is a homomorphism from L to K, then the kernel of phi is an ideal of L, and the image of phi is a subalgebra, let's not forget our spelling here, of K. And so this is a pretty straightforward check. So we want to, I'll leave it to the viewer to check that the image of phi is a subalgebra of K. I'll show that the kernel of phi is an ideal of L. It's like a two-line proof. So if we want to show that the kernel of phi is an ideal of L, then what that means is that for all x in your kernel, and for all y in your Lie algebra, x bracket y should be an element of the kernel. Right? So what we want to show is that 0 is equal to phi of x bracket y. This is what we're not sure about, okay? But we know phi is a homomorphism, so we know that this thing here is equal to phi of x, phi of y, and then we know phi of x, well, x is in the kernel, so this is equal to 0 with phi of y, which is equal to 0. And so that tells us that x bracket y is in the kernel. And so that in particular tells us this, that the kernel of phi is an ideal. Now by similar proof, we can see that the image of phi is a subalgebra of K. So let's come back up to here and see what the kernels of these maps are. Okay, so in the first example, I hope it's trivial. The kernel is L here. So kernel of theta is equal to L. In the second example, well, this map is the trace map, and so what are the maps, what are the matrices that have trace 0? Well, by definition, that's SL and C, right? So our kernel of the trace is equal to SL and C. Okay? And then lastly here, for the canonical map, the kernel is just your ideal. So the kernel of pi is equal to the ideal. Okay? And I hope that's also straightforward. All right. With that being said, let's take a look at a very, very common theorem in our general study of abstract algebra, which are the isomorphism theorems. So let phi be a homomorphism of Lie algebras from L to K, and let I and J be ideals of L. Then the following hold. L mod the kernel of phi is isomorphic to the image of phi. So recall that the kernel of phi we just saw as an ideal, and so we can quotient it out, and so we have that this is actually isomorphic to the image. Okay? Second, if I is sitting inside of the kernel, then there exists a unique homomorphism psi from L mod I to K, such that this would be the other way around. Psi of pi is equal to phi, where pi is the canonical map. And so diagrammatically what this is saying is you have this map L into K. This is phi. What we're doing is that if you want to go into K, you can actually bypass into L mod I via the projection. And then there's a unique map psi such that we can go back into K. Okay, and the key condition here is that I sits inside of phi. Okay, the kernel of phi. Otherwise, it wouldn't make sense. Like it just wouldn't be true. Okay, so I hope that's clear. third is that if I as an ideal sits inside of J, then J mod I is an ideal of L mod I, and L mod I quotient out J mod I is isomorphic to L mod J. So this is kind of interesting. If someone who just knows division might be like, oh yeah, it's obvious, you know, you just cancel out the i's. Oh, I guess that's one way to think about it, but that's not really how it works. And so this is kind of cool. And finally, D, you have I plus J mod J is isomorphic to I mod I intersect J. And so I leave it to the viewer to check these. These are standard exercises in abstract algebra. The novel thing about the proof will be the bracket and how that plays in here. But everything pretty much follows pretty similarly. But what I do want to look at is this guy here. We'll prove this by example, kind of. We'll come back over here. So L mod the kernel is isomorphic to the image, right? So let's see if that's true. So in this example, the zero map, well, L mod the kernel is just going to be L mod L, which is just equal to the zero vector space. So this is indeed isomorphic to K, which is the image. So we have verification there. In our second example, right, we have GL and C is going to mod its kernel, which we said the kernel of trace is going to be SLNC, right? We know that that GLNC has dimension n squared and SLNC has dimension n squared minus 1, and so this is isomorphic to C, and of course the trace is a surjective map. So in particular, we can call this an epimorphism. So I'll call this an epimorphism in the terminology above epi. Okay, and so the isomorphism theorem holds here, and then lastly, it's going to hold here. I mean, that's just by definition. The canonical map is precisely the map which sends it, the ideals, sends L to the quotient algebra. All right, so I hope that proof by example is sufficient to convince you to do the exercise. All right, so those are our kind of elementary results, and with that being said, we can actually define what we set out to define, which is a representation. So a representation of a Lie algebra L over a field F is simply a pair phi comma v, where v is the vector space over F, and phi is a homomorphism from L into the general linear algebra of V. So really, all a representation is it's just a homomorphism with a specific destination, okay? And the destination can vary, but it's always going to be a general linear algebra. And the idea here, at least the way I like to think about it, is that like we like linear algebra, and we like matrices, and we like these concrete examples of matrices. And so the whole idea of the representation is to go from something abstract, from your Lie algebra L, into something we can work with, which is GL of V. Now I'm sure there's more nuance to it, but that's like the general way I like to think of it. And so as a remark, let me change color back to black here. If this homomorphism is injective, if phi is injective, we say this is a faithful representation. Okay? So now let's take a look at a couple of examples. Okay? We already saw an example with the zero homomorphism earlier. The zero homomorphism, right? Theta, which goes from L to, so in this case, it's going to the complex numbers, right? And the complex numbers can be thought of as the GL1C, right? They're the GL of V, where V is one-dimensional vector space. Okay, so that's why that's a homomorphism. It's a representation, sorry, and it's called the trivial representation. So the trivial representation. Okay, and it's called a trivial representation because, well, it's trivial. The second example is the natural representation. Okay, the natural representation is simply one that goes from Well, we already know that if L itself is equal to GL of NC, right, or GL of V, well, then there's a natural representation which just sends everything back to itself, the identity map, right? So I'll say the identity map on L equal to GL of NC, okay? And then lastly is there's, well, not lastly, but the last one we'll talk about today is the adjoint representation. Adjoint representation. Okay, and so recall that we actually already looked at this. This is the map add that sends L to GL of L, where we look at L as a vector space. And so this map is actually kind of, this is the gold standard of maps. This is the map we'll always talk about. And so let's actually check that this is a homomorphism. And so first of all, we know that if we basically what we need to check in order for it to be a representation is that it's a homomorphism, and we already know it's a linear map, so we just had to check that the bracket condition is satisfied. And so what we're really saying, right, is that we need to check the following. For all, so for this guy, the adjoint sends vectors in L to GL of L. So what we need to check is that if you have add x and add y, where x and y are elements of L, then we're wondering if this is equal to add x bracket y. Does this make sense? Like add is the map, right? But the thing is, on both sides of the equation, we have linear operators. So the way we're going to check that they're the same linear operator is if their value on any arbitrary vector is equal, they agree on that vector. So we're going to say for all z in L, we're going to see what happens if you act on z. So on the left-hand side, right, because this thing sits inside a GL of L, we'll just use that bracket. So this is add x, add y, minus add y, add x, acting on z. And then we're going to, let's put our z here. And so this thing is actually equal to, by definition of adjoint, x bracket y bracket z minus y bracket x bracket z. And this thing here is equal to x bracket y, the quantity bracketed with z. Now if you look at this close enough, right, this is just the Jacobi identity, right? This thing is equal to that thing by the Jacobi identity. So it's actually true for all x, y, and z. Okay? And so immediately follows that this is a homomorphism, and because it's going into GL of L, where we look at L as a vector space, it's a representation. And so, as I said, this will be one of our most important representations. And to come back here, the book makes a distinction that for all our purposes, L will be finite dimensional. So finite dimensional. All right. Okay, just one last remark before we can end this video is that the map adjoint, I always like to make this clear. I made it clear in an earlier video actually. The adjoint map is a representation, but the map add x, where you fix x, and this is not a map from L into GL of L, this is actually a map from L into L, is not a representation in general. And an easy way to see this is that, I mean, it's certainly linear, but it doesn't preserve the bracket in general. And the way you can see this is if you say S is equal to SL2C, so let me disclaimer, not a representation. If you have SL2C, right? Let's take the vector H, right? If we want to see if add H is a representation, then what would need to be true is that for all P and Q, this should be true. So for all P and Q in L, which is SL2C, we should have add H acting on P should equal add H acting on Q. And that's not true, because if you take P equal to E, remember E the basis vector, and you let Q is equal to F, the other basis vector, then what you have here is that you have H bracket E bracket F question mark equal H bracket E H bracket F. Okay, this guy is going to be equal to H bracket H, and it's going to equal 0 like this, whereas this guy is going to equal 2E bracket minus 2F, which is minus 4H. And these guys are not equal. So the adjoint as a representation, that without fixing an X as a representation, but if you actually consider a specific element, it's not. Okay, so that was just to clear any confusion, because I know early on I kind of confused the two. Alright, so that will conclude this video. Thank you for watching.